field talks about using data, leveraging data to make their business decisions. But in spite of such a maturity of data science, still there is a lot of ambiguity around what data science is and how we can use data science and how we can try to build projects using data science. To get this clear, first one has to understand the introduction, the basic concept behind this approach, what we call as data science. So today, the main part of the agenda is to set that introduction. What is data science? Where do we
Sir,
use
sorry to
data
disturb
science?
you. Can we go for full screen?
Yes, I can.
Yes, thank you.
So what is data science? And where are we using it? And if we have to build a application, or if we have to build a project in data science, what are the steps involved? What is the approach that we are going to take? So that's going to be the main discussion for today, the day one. From day two onwards, we would see a lot of practical sessions, some kind of demonstrations, and some kind of writing programs, codes, etc. So day two is going to introduce you to Python as a programming language. Python is an open source and very powerful programming language, popularly used across different software applications. But in the field of data science, Python has been the single most programming language which has been very, very popular and widely used across the industry. But having said that, Python is not the only programming language that we can use or we can take help from to build data science applications. There are a ton of other programming languages also. To name a few, R is another programming language which is as good as Python. It's like almost similar to Python, but it has its own way of syntax, its own way of execution, etc. So the reason I choose Python for this demonstration is it is a general purpose programming language, not only for data science. You can look at Python and usage of Python with a wide variety of software applications. If you want to build a web server, or if you want to do some application programming, you can do pretty much everything using Python. So Python has almost become a very widely used general purpose programming language. And in the field of data science also, Python is probably at the #1 position when it comes to the usage of different programming languages. And it's completely open source. You do not have to pay or you do not have to buy any kind of licenses to use this. So if you have a laptop, you can pretty much go to the website which has Python installation files, get the Python installed for you, start using it right away. Even it is for your toy projects, educational projects, or even it is for building some sort of commercial applications, Python is absolutely free for you. So that's the reason why I choose Python as the main programming language to go over this workshop. So tomorrow we will spend a lot of basic steps in installing Python. How do we use Python as a simple programming language? What are the basics of Python? And then go into some of the most important concepts called modules and packages, and the most commonly used module called as pandas. So this is where I expect all the participants to help me out with some sort of pre-reading material, pre-work that the management has shared with you. Introduction to Python. I shared a 4-hour video. If possible, by tomorrow, you try to complete that 4-hour video before you attend this session, so that it would be much more easy for you to follow the concepts. From day 3 onwards, that's exactly the core of data science that we are going to see. And through this workshop, I want all of you to set up into a path of data science where you are going to shine as data scientists in your future career. That's my most important objective. By the end of this 5-day session, I want all of you to have complete clarity on what is data science, where to start with if we have to become a data scientist, what are the concepts involved in data science, what tools, technologies that we have to learn eventually if we have to become a data scientist. So that's my main agenda for this particular workshop. Of course, in this 10-hour workshop, I may not be able to cover each and everything in data science. Data science is definitely a very long journey, and it has a lot of different concepts involved in it. But in this 10-hour workshop, we are going to see some of the very high-level topics within data science. And one of them is called as predictive analytics. I would speak a little more about predictive analytics in a short while when I start my day one lecture. But to just give you a glimpse of what we are going to see day 3, day 4, day 5, we are going to see some of the concepts that are very, very popular in the data science world, called predictive analytics and different types of predictive analytics, how to perform them, and the three models that we are going to see is called as linear regression, one of the very basic but very popular technique in the field of data science, then classification, and then clustering. Meanwhile, I want to give some of the instructions to the participants so that we get the best out of it. I know all of you have been muted because we have a large number of audience present in it. So allowing people to speak is definitely not going to be fruitful. So if you have any questions, feel free to post your questions on the chat window. You can see a chat window at the bottom. You click on the chat window. You can post the questions on the chat window. I'll keep a tab on all the questions that are coming in. I'll try to answer them right away if it is the appropriate time to answer, or else I will try to keep a note of the questions that are coming up, and I'll try to answer them by the end of the session or at the appropriate time. Okay, so don't hesitate. Let's make this interactive. Let's make this interactive by posting your questions, and then we would get the best out of this particular session. So that's one instruction. Second, I would switch between my presentation and a whiteboarding. For example, if you could see my screen, this is a whiteboarding session where we could just write anything, and most of the concepts that I'm going to explain is going to be done by this whiteboarding session. And if there are any important points, please feel free to make a note of them, because that's going to be very useful. Even after a month, if you have to go back and refresh yourself to see what concepts have been discussed and what are the important further reading concepts that you may have to look at, then you probably take that as a notes and use the notes for your preparation going forward. Now, with that, let's directly jump into the today's learning, and we're going to learn different concepts within data science today. I hope all of you can see my screen. If not, do post it on the chat window. Now, what exactly is data science? Maybe you may not have realized it, but you have already been using a lot of data science or data science based applications, be it on your smartphone, be it on some of the web pages that you regularly use, etc. A simple example of a data science can be your email applications. Most of you might have started using emails already, so you know how a simple email application would work. In your email, irrespective of whoever is the email service provider you have, like Gmail or Yahoo Mail or Hotmail, so many different types of them, you have two different types of inboxes. Like there is a regular inbox and there is one more called as spam box. Some of the emails would land into your inbox. Some of the emails lands into your spam box. So these are the two type of boxes that we have in our email applications. Now, someone sent you an email and you have received that email. The service provider has to decide whether to put this email into a spam folder or to put this email into a inbox folder. Now, how do they decide the email that you have received from a sender, and this is the server side, and the service provider has to decide whether to direct that email to your spam folder or to send it to your inbox? This type of decisions are being made with the help of data science, and that's what we are going to learn through this workshop. Fine. What are the different types of data science? The most popular one, which we are going to see through this workshop, is called as the predictive analytics. The name itself says we are going to predict something that's about to happen in future, and based on that prediction we are going to make some decisions. So the other name for data science is also called as decision sciences. Why? It will try to help businesses to take decisions by knowing something that's about to happen into the future. So that is why another name for this is decision science. Though data science is probably a very simple and common term that is in usage, and very recently we are also talking about a new term called as artificial intelligence, AI. And how is this related to data science? Of course, there is a relation, okay? And during our last day's session, I would also spend a little more time talking about AI and how is it related to data science, etc. For today, let's start with the predictive analytics, the main part of data science. It's divided into two types. One is called as supervised learning, and the other one is called as unsupervised learning. Now, what is supervised learning and what is unsupervised learning? Supervised learning means learning through examples. Learning through examples is typically called as supervised learning. And unsupervised learning, yes, we do have some data here, but we may not have something called as a outcome variable. Of course, it would be confusing at the beginning. Don't worry about it. I'll give an examples of both of these so that you understand clearly what is the difference between supervised learning and unsupervised learning. Okay? Fine. Let's say you want to resell a car, or you want to buy a resale car. Either you want to sell your car or you want to buy a resale car. Next question is, you saw a car. Now, what is the price of this particular resale car? You don't know because you are not an automobile expert by yourself, or you are not a service agent. A service agent or a automobile expert might know or might guess what can be the price of this car. But if we are not familiar with automobiles a lot, we would probably not able to guess what would be the price of a resale car. Now, let's say someone built a portal like this, a web portal like this. You have a lot of web portals like this. That's why I'm using this as an example, where you could go and enter some details about the car, like what is the model of the car, what is the year of the car, year of manufacturing, and what is the odometer reading of the car, like how many kilometers this car has been driven already, etc. So these are some of the fields. Now you enter some details. Let's say you enter some details like XYZ 2015, odometer reading is 50,000 something. And then the moment you submit this data, it gives you a result saying that the price of the car. And let's say it guessed the price of the car as 2,50,000. And this is the price guessed by this web page. Now the question is, how did this web page came up with this price, and what is the science behind this? That's exactly what we call as a supervised learning. So whoever has built this portal has used data science to learn how to decide the price of a car, and from that learning they have built this portal which enables anyone to just go and submit some data and get the price of the car. And by the way, this is a guessed price. This is a predicted price, not guarantee that you would be able to sell this car for exactly 2,50,000. So this is a rough estimate of the price that this particular car can fetch. Now, having this rough estimate, now if you are trying to sell this car, you probably quote something like, let's say 2,60,000 as the price. The buyer might negotiate a little bit and might buy the car for 2,50,000. Now, if you are the buyer of the car, now you know the car details. Now you enter this car details. The predicted price that the portal has shown you is 2,50,000. Now, it is a rough estimate that you have in mind. Now, when you start negotiating with the seller, okay, it's roughly around 2,50,000. That's probably the moderate price. Maybe let me start with 2,40,000. Let me make an offer for 2,40,000, and maybe the buyer will also negotiate and try to maybe settle somewhere around 2,50,000. Okay, so this price that is given by this portal here is a prediction. Then, how did they came up with this particular prediction? So this is exactly what we call as the data science, and that's what we are going to learn how to do this. Another good example for you to understand the applications of data science is, most of you might have used Google Maps, right? So when you use Google Maps, especially the directions, you don't know the route. When you are in a city, especially, you definitely rely a lot on Google Maps. You give your starting point and you give your destination. The Google Maps is going to guide you to reach from the starting point to the destination. It gives you instructions like, okay, take the left in the next 500 meters, continue there for like 1 kilometer, take right. So that's how it tries to give instructions and guide you from the starting point to your destination. Along with it, it will also give you something like what would be the estimated time of travel before you start. Okay, I'm starting at 4 p.m. and the moment you start, it will tell you, hey, given the traffic and the distance that you are about to travel, you may reach your destination at 4:50 p.m. and it gives this right when you are about to start. It's not waiting for your journey to complete to decide the price. It just tells you it is going to take 50 minutes for you to reach the destination. Now, how did Google Maps came up with the estimate of travel time? That means what time you are going to reach your destination. This is also a kind of prediction. So we are predicting what would be the travel time of your journey, of your trip, based on your starting time, your destination, and the traffic in that area. We are predicting this trip is going to take 50 minutes to complete, and the 50 minutes of travel time here is nothing but a prediction itself, right? So these are all applications that most of us might be using already, but doesn't realize what is going to happen behind the scenes. And that's what we are going to see through this workshop. Fine. There is a question on what is the difference between machine learning and data science. The crisp answer here is there is no difference. Data science is a concept, and to perform data science, we need a lot of different types of algorithms. And those algorithms are classified into few different categories. Let me write them. Fine. Now we want to predict this travel time over here. How can we predict this travel time? So this is the question, okay? Let me take a new sheet. So we want to predict something, whatever be the prediction, okay? We want to make some predictions. So how do we make this prediction? To make any type of prediction, we first have to learn. For example, if you have heard some stock market experts speaking on different news channels, they also give some type of predictions like, okay, by the end of this month, stock market, maybe NSE, National Stock Exchange, is going to reach 10,000 points. Now, how did they came up with that prediction? By the end of this month, stock market is going to reach 10,000. That type of predictions are typically made using domain knowledge. Domain knowledge in the sense, they have spent a lot of time to understand how stock markets operate and what are the fundamentals of the stock market, how different political events, business events are going to affect the stock market, and based on their knowledge, they are coming up with this type of predictions. But in the field of data science, we are going to learn to make predictions by learning from the historical data. Now, let's say I want to build that. I'm talking about supervised learning here. Unsupervised learning example I'll give in a little while. So we are looking at the supervised learning example. So we want to predict things. So to predict things, first of all, we have to learn this from the historical data. Without learning, yes, we cannot make prediction. But learning the domain knowledge and making predictions based out of the domain knowledge is a very, very lengthy process. It probably would take years to get to learning the domain knowledge and try to make use of that learning to make the predictions. And in most of the cases, it may not be accurate also. We have seen a lot of stock market experts making a lot of predictions, and majority of them didn't really turn out to be true. Yeah, prediction is always a risky business. Not every prediction is going to be right. Now, in the data science approach, this is how we are going to do. We call this as learning through examples from historical data. I want to build a portal which can predict the resale price of a car, which can guess the resale price of a car. So for that, how do we have to learn from the historical data? Let's say we collect the historical data like this. Model of the car, make, who is the manufacturer, odometer reading, manufacturing year, insurance status, claims. All of these are called as features. In the database terminology, you could probably call this as columns. And the resale price. Let's say we go to some of the car resellers in the city. They might have sold a lot of resale cars in the past. Let's try to collect the data from them. Observation number 1. Model is, let's say, XYZ. Make is ABC. Odometer reading is 50,000 kilometers. Year of manufacturing is 2015. Insurance is valid, or maybe valid in terms of months. Let's say it is valid for next 3 months. Claims, claim amounts. Let's say the past claims of the insurance is 25,000, because the claim amounts in the past will tell you if this car has been involved in any type of major accidents. If there was a major accident, then the claim amount would be very high. If there was no major accidents, this claim amount would be very, very small, right? So this is the domain knowledge that we are talking about. And I do not want any domain knowledge, right? Now, this car got sold for 2,50,000 rupees. Observation number 2, 3, so on, up to, let's say we got 10,000 cars. So we got the data for 10,000 cars. This pretty much looks like a table for us. So we have collected the data in the form of a table. Now, this variable over here, this column over here is nothing but the outcome. We want to predict it, and it will be represented using Y. And these columns here, these variables here, I would be using variables a lot of time, because in the field of data science, we call them as variables rather than columns. So these variables here are input variables, and we represent them with the help of X. So these are all the input variables that we have, and this is the target variable Y we have. Now, using this data as examples, we want to learn how can we make predictions of the resale car prices into the future. Now, a car comes into the garage of a car reseller. It is, let's say, XYZ, and the manufacturer is ABC. Odometer reading is 25,000, and year of manufacture is 2018. Insurance is valid for 6 months, no claims. Now, what would be the resale price of the car? We have to predict this. Now, to predict this, first we have to learn from this historical data. So, learning from historical data, learning through examples, is typically what we call as the supervised learning. Now, how can we learn from the historical data? We need a lot of mathematical or some sort of algorithms that can learn from this historical data and make these predictions into the future. So the learning is going to happen using different types of algorithms. The first set of algorithms starts with the concepts of statistics. So they are called as statistical algorithms. The next set of algorithms starts with data mining techniques. So in your undergraduation or in your post-graduation, you might be coming across some concepts of data mining like decision trees, etc., etc. So those are called as data mining algorithms. And the most heavily used set of algorithms in the industry today is called as machine learning. Now, machine learning is a combination of these two. They are very powerful, they are very informative, and they are very fast compared to these ones. So, in the world of data science today, if someone says, or if someone claims that I am a data scientist, what they mean is they're using a lot of machine learning algorithms to learn from the historical data, and from that learning, they can make predictions into the future. That's exactly what machine learning is all about. Now, data science and machine learning are not two different fields. They are the very same fields. It depends on what type of algorithm that we are going to use to learn from the historical data, and through that learning, we can make predictions into the future. And today, most of that learning is going to happen through machine learning. So that's why this industry is simply also called as machine learning. Don't get confused. It's the same. Next, the most advanced ones in the industry today are called as deep learning algorithms. Now, if you are not familiar with this term called deep learning, don't worry about it. Learning from different types of data will throw different types of challenges at us. For example, take this. Your Google Assistant or your iPhone Siri, your Amazon Alexa, all of this can take your voice instructions. If you say, hey, okay, Google, call some person, and if you name the person, Google would try to find out, the Google Assistant will try to find out that person in your contact list and makes a call. Now, did you ever wonder how did your phone understood the language that you are speaking and able to take action from it? You are giving a voice command to it. First, it has to understand the voice command. Then it has to take some action. So understanding that voice command is going to happen through learning, and learning in those type of scenarios, and we call this as unstructured data. So if you see here, this is also a learning example. We are trying to learn how to predict the resale price of the car by using some historical data. But this historical data is a very much structured data. When we say structured data, data that is typically stored in rows and columns. It could be a table, it could be an Excel sheet, or it could be in any other form. So if we can arrange the data in the form of rows and columns, that's called as structured data. Learning from structured data is pretty easy, and for those type of learning, we mostly use machine learning models. So when we are trying to learn something from the structured data, we typically use machine learning. When we are learning something from unstructured data like voice, text, speech, video, images, all of this is done through unstructured data. So all of this is unstructured data, and learning something from unstructured data is typically done through deep learning. And this is the industry which we are calling as artificial intelligence. Artificial intelligence is a very broader term. Training a robot is artificial intelligence. Trying to find out new stars in astronomy is also done through artificial intelligence, etc. Right? So it's a very vast field. When it's related to data science, the learning that happens through the unstructured data, and from that learning, if we can take some decisions and take some actions, that's exactly what we refer to as artificial intelligence, right? Fine. I'll give you some of the applications of artificial intelligence. The first and the foremost application of artificial intelligence is voice recognition or speech recognition. Your Google Assistant, iPhone series, etc., are examples for that. You speak and it understands and it takes action on top of it. Next one is image recognition. So a lot of people might have heard this term called as computer vision, which is a kind of training computers to learn something from the image data and take actions, etc. So that's a very, very popular field these days. Computer vision is a very popular field in the artificial intelligence. Then how is it done? How is computer vision done? Again, using artificial intelligence. For example, most of you might be using smartphones these days, yes. And your smartphones are capable of taking beautiful pictures. They do. Now, instead of a smartphone, if you give a digital camera to the same person and ask that person to take the photo using a digital camera, the picture that is taken through a digital camera compared to the picture that is taken on a smartphone, the picture on the smartphone would be very clean, everything perfect. In just a single click, you get the perfect photo out of it, but may not be the case with the digital camera. Why? To take a beautiful picture out of your digital camera, you need to learn the art of taking a photograph. You need to understand a lot more mechanics on how your digital camera really works out. But that's not the case with your smartphone. You just open the camera, click the picture, and right away it looks beautiful. How is it possible? It's possible because a lot of AI, the computer vision modules, has been used and built into your smartphone, which would auto-correct majority of the things that is not so good in when you are actually taking the picture. If the light is not so good, if the exposure is not so good, everything is automatically adjusted by itself. Now, how does your smartphone know that for this scenario, this is the best output of a photograph and it automatically corrects it? That's through the computer vision, right? We probably don't have to get that far right away at the beginning stage of it. Let's try to learn with very simple, basic examples in the next 5 days. And I'm sure most of you are going to get motivated to learn further. And I can give you a lot of instructions on how to proceed further, what topics to learn. Eventually, I would want all of you to become very successful in your data science careers. Okay. Now, coming back to the topic, the supervised learning. Here, this is what we are trying to predict. This is what we are trying to learn from the historical data and predict. The variable that we are predicting here is a continuous number, like 2,50,000. 1,80,000, 4,76,000. So these are typically called as continuous numbers. So if you are trying to predict numbers, continuous numbers like this, that type of prediction is called as regression. So this is named a very simple but very popular technique that we use. Whenever we are trying to predict a variable that is a continuous numbers like this, that is called as a regression. It is still part of your predictive analytics. We are still predicting a variable, but we are predicting a variable on a continuous scale. That's why the name is given as regression. So in this workshop, we are going to learn an algorithm which is called as linear regression. And through this linear regression, we are going to learn from some historical data like this. And using that, we can make predictions into the future. So remember this, make a note of it. So supervised learning is divided into two types. One is called as the regression. The other one is called as classification. So what is regression? When we are learning from the historical data and we are trying to predict a variable that is continuous numbers, that problem is called as a regression problem. Sometimes our prediction can be discrete. What is a discrete prediction? Whether it will rain tomorrow. Yes or no? How much it is going to rain doesn't matter. We are simply predicting whether it will rain or not. So the answer here is a simple yes or no situation. So that type of predictions are called as classification. I will spend a lot more time on classification in a little while. Before that, let's complete this regression and then we go further and try to learn about classification. Fine. Now, what's our approach? Our approach is going to be like this. So we have this historical data. We would try to divide this historical data. Our historical data are 10,000 observations. 10,000 observations which has all input variables and the target variable in it. From this 10,000 observations, we are going to learn and make predictions into the future. But first step in our approach is dividing this data into two portions. Typically 80% and 20%. It doesn't have to be 80-20 all the time. Sometimes it could be 90%, 10%. It could be 70%, 30%. Depending upon the volume of data that we have, we would divide this data into two portions. And this division is going to be done purely on a random basis. Like some of these observations out of 10,000, some of these observations will go into the 80%, some of these observations will go into the 20%. But if we take it like this, first 8,000 observations separately and next 2,000 observations separately, that is not a random selection. Random selection is we have 10,000 people, we ask 8,000 people to one side and 2,000 people to another side, and it has to be purely on a random basis. How we can do that? We can do that with the help of some simple code. Out of 10,000 observations, how to randomly select 8,000 observations. I'll show that with the help of a simple Python code later. So don't worry about it. Now this 80% of the observations here are called as the training portion. This 20% observations here are called as test portions. I see some of the participants raising their hand. I'm not sure whether you have a question or you are asking for something else. Please post your question on the chat window so it would be easy for me to answer your questions. Unfortunately, I'll not be able to talk to you person to person. Only way is to get help with the help of chat. Machine learning is required for data science. There was a question asking, is data science required for machine learning? It should be the other way. We can perform data science. Data science is a broader concept. It's an objective. We want to predict future. Simply, that's what data science. We want to predict something that is about to happen into the future. And to do that, we need to learn from the historical data. To learn from the historical data, we have to first choose what type of algorithm that we are going to use to learn from the historical data. And these are the broader sets of algorithms that we can choose from. Okay. Yes, data science and artificial intelligence are very much related. They are very close. Probably you could call them as twin brothers. Okay. Artificial intelligence is the latest kid in the market, right? But before that, it's data science. Now, that's why I clearly explained the difference between these two. Artificial intelligence is more of trying to build applications that uses a lot of unstructured data, voice, image, speech, text, etc. Machine learning, the field that we simply refer to as data science, is also learning, but typically learning from the structured data. That's a broader difference. Yes, but I cannot separate data science and artificial intelligence from each other. There is a huge overlap between these two. Probably some of the people say data science is a subset of artificial intelligence, and that's very much acceptable. They are kind of twin brothers. They belong to the same field. Okay. Fine. Now, coming back to the need for having a difference training data and test data. Very good question, right? Okay. Now, if you have an algorithm and you learn from this algorithm and you are ready to make predictions into the future, but how do you know whatever the learning that is made by this algorithm is really good or not? For example, I'll give you a textbook and I'll ask you to learn something from the textbook. Now you come and tell me that, hey, my learning is done, I'm ready. Now, how do I know how good your learning is? I want to put you to a test. Through the test, we are going to measure the performance and judge how good the learning is. That is the reason why we have a train set and a test set. Again, why to have a separate test set? Why can't we learn from all the 10,000 observations and use the 10,000 observations for testing again? Like both training and testing are same examples. That's not allowed, and there is a reason for that. So in a layman terms, let's say we have a subject and we are learning that subject from a textbook, and in that textbook we have a lot of solved examples. Now in the test paper, if I take the solved examples from the textbook as it is and give those questions in the test, many people would perform very well in the test, naturally. Why? Those examples are the same examples that are solved in the textbook. So people who have read them, instead of trying to understand the logic of how to solve the problem, simply by-hearted it and memorized it. When they see this question on the text paper, they don't even read the question completely. First line, I know this question was there in the textbook, and they start dumping the whatever that they remember, the solution from the textbook as it is. And do you really call that as learning? No, that's memorization. Learning means trying to put a valid logic, whatever be the logic, to understand the problem and we understand the approach of solving the problem and apply it on the new problems. Now, instead of giving the same examples as it is what is there in the textbook, I give some of the examples which are very similar to the problems that are solved in the textbook, but the numbers are not same, they are slightly different. Now, only the people who have understood the logic of how to solve the problem will be able to give a solution in the answer sheet. Otherwise, no. That's the right learning. Similarly here, an algorithm can also cheat us. How? If we use the same data for training and testing, let's say this observation here is used in the training, Now the same observation is given in the text. The algorithm has seen this observation already. It memorized it indirectly. Now, the moment it says, okay, car model is XYZ, make is ABC, odometer reading is 50,000, I know this observation. The resale price was 2,50,000. Let's go and give that as a prediction. And you make perfect prediction, but it's kind of cheating. You try to memorize the data, and based on that, you give a prediction. If we do so, on this data, we may be doing a good job. On this data that it has used to learn from, it might do amazing predictions. Now you give a new car something like this, it gives you a prediction of, let's say, 1,15,000, which is way far from the reality. What happened? On the training and the test data, the learning was very good. The model really performed very well. But on some unseen data here, when we give a new observation, it is giving us some bizarre predictions, not the right predictions. That's because of the biasness in the training and test. When you learn from the same examples and when you are tested on the same examples, that's not proper testing. A proper testing is learn from some examples, perform well on similar examples, but different examples, the examples that the model has not seen, the examples that we haven't seen in the textbook. Now I am more sure that you have really learned the logic of how to solve this problem. Now I am more confident you are going to make good predictions, better predictions. Now I have trained you and I have tested you. On the testing, you have been giving good predictions for me. Now I am more sure if I use this learning, if I use this model, learning is called as model. We would see what a model is a little while later, tomorrow. But simply today, learning is nothing but a model. When we use that model to make future predictions, we are going to get good set of predictions. We are going to get accurate predictions that is very close to the reality. To remove that biasness of memorizing the data, we are going to have a separate set for training, separate examples for training, and separate examples for test. Fine. Next question is, what are the data sources used in data science? Data comes from different shapes, different sizes, different forms. So it doesn't really matter what is our data source. 80% of the times, our data source will be a database. It could be a simple RDBMS like MySQL or something. In some cases, it could be a database which is NoSQL databases, document databases, etc., MongoDB, CouchDB, PostgreSQL, etc. Right? So databases are very different. Data sources are very different. We do not have to learn everything about our databases and data sources as a data scientist. Okay, as a data scientist, we are more interested in how do we learn from the historical data, and from that we are going to make predictions into the future. That concept is more important for us, right? But for you to answer your question, data can be coming from different sources. Sometimes it may not be even a database. For example, if we take a few resumes, if someone has 1 lakh resumes, that's text data, pure text data, and it's not stored in any database. It's just blindly dumped into a folder, into a directory. We can do a lot of data analytics. We can do a lot of data science on text data as well. That is also a data source. It's just a bunch of text documents for us. It could be a bunch of PDFs for us, right? So our data sources are going to be wide variety. Fine. The next question is about logistic regression. Maybe you jumped up a little ahead. Logistic regression is a model is an algorithm typically used to perform classification. You will be learning logistic regression as part of this workshop. It may come on the 3rd day or on the 4th day. So you could clearly see how to perform logistic regression, how to perform classification through logistic regression on the 3rd or the 4th day. Okay, wait for it. Fine. What is a data warehouse? Explained. I may not be the expert to talk on data warehouse. The reason is data warehouse is altogether a different concept than data science. Data warehouse falls into what we call as data engineering. To give you a brief explanation of what data engineering is, data comes from a wide variety of sources. Someone has to collect the data, maybe transmit the data, clean the data, transform the data, load the data, and store it in a place which is accessible for different applications, or which is accessible for different business decision making. So this whole process of starting from the data creation to data cleaning, transforming, loading it into a database, organizing it in a way that it is easy to access, and helping some sort of business decisions making is typically an ecosystem by itself. And this ecosystem is what people refer to as a data warehouse. So it has pipelines built into it, which could collect the data from the source. It has ETL logics built into it, which could clean the data, shape the data very well. It has different databases within it, so that different types of data is stored in different types of data sources. A lot of new data is defined, and every day the data is accumulated and the data is being constructed. So these are all typical pieces of data engineering, and data warehouse is a part of that. I am an expert on data science. I'm not a data engineer by myself. Yes, of course, I do work a lot with the data engineering team, so I know at a high level what data warehouse is, but that's probably a out of concept question for this particular session. Okay, yeah, that gives you the high level overview of what data warehouse, what data engineering is all about. Fine. Now, yeah, there was a question on the train and test data sets. Let me complete the next topic, and I hope that would answer your question naturally. If not, I'll try to get back to this question and try to answer it again for you. Fine. Now, we have, let's say we used a algorithm, this algorithm here, linear regression. To this algorithm, we pass this data. How to do it, we would see in the practical demonstration. Let's say, imagine we did that, and this algorithm has learned and it is ready to make predictions. Now, the learning happened on this 80% of the data. And for the remaining 20% of the data, we ask the algorithm, we ask the model to predict the resale prices of the cars for this 20% data here. Okay. Now, for this 20% of the data, we have Y values, like first car 3,80,000, second car 4,20,000, so on. These are the actual prices the car has got sold for. But when the algorithm tries to predict them, predictions are always represented by the symbol Y hat. Anywhere when you see symbol like Y hat, Y cap, that means that is a prediction. Why? is the original value, the actual value. Y hats are typically the predictions. Let's say for this car, the algorithm, the model predicted the price as 3,70,000. And for this car, the model predicted the price as 3,40,000. If you see here, there is a difference between the actual value and the predicted value. Actual value the car has got sold for is 3,80,000. What the model has predicted is 3,70,000. Second car, the actual price for which the car has got sold for is 4,20,000, but the model has predicted the price as 4,30,000. Look at the difference between these two. They are very near. There is a under prediction, less prediction of 10,000 rupees here. There is a over prediction, higher prediction of 10,000 rupees over here. So that means there will be some difference between the actual price and the predicted price. But if the difference is very negligible, like this, when the prices of the cars are in lakhs, like 3,80,000, when the model has an error of only 10,000 rupees, that's absolutely fine. But for a given car, something like if the predicted actual price is 5,20,000, if we predict this as 4,20,000, this is not okay. This is a huge error. So this observation here is not good. Maybe these two observations here are pretty good enough. So this is a good prediction, this is a good prediction, but this is a pretty bad prediction because the actual prices of the car is 5,20,000, but what the model has predicted is only 4,20,000. So this is not acceptable. Now, if there are 2,000 cars, we cannot look into each and every observation to check if the prediction is very close to the actual or not. So it's impractical. So for that, we need to assess the performance, how good the learning of this algorithm is. We are going to introduce something called as performance measures. So using this performance measures, we can try to see if the model is really doing a good job or not. We call this as error metrics. So using this error metrics, let's try to decide how good this model predictions are. To bring this error metrics, you first have to compute the difference between actuals and predictions, and we call this as errors or residuals. The other name is residual. The common name is errors. For each observation, there will be an error. So this is 10,000. This is the error for first observation. For the second observation, it is minus 10,000. And for the third observation, it is almost 1 lakh. So this is the error, right? So we have got different errors. Now, let's say we compute the average of all these errors. But to compute average, we have a sign problem. Some of them are positive, some of them are negative. To compute averages, generally we sum them up. So sum of these errors and divided by the total number of observations, typically n. So this is how we compute the average. But we sum them up, if we sum them up directly, because of the negative values and the positive values, this would get nullified. So to avoid that, what we are going to do is take the absolute value of it. Okay, so we call this as mean absolute error. So there is a difference between the actuals and the predictions, and we take the absolute values of those errors and we can compute the average of that. So that is why it is called as mean absolute error. Mean is nothing but the average. So mean average of absolute error. So we are not taking the sign into the consideration. we are taking the magnitude into the consideration. Now, if this is a small value, let's say the mean absolute error is 10,000. So that means on average, when we make the predictions of the car price, we are wrong by 10,000 rupees. That's okay. When the predictions are in the range of 3 lakhs, 4 lakhs, if we make an error of 10,000 rupees, that's not a big deal. That's okay, right? Another way to measure the error is called as RMSE. It's called as root mean squared error. So how do we compute this? To compute the root mean squared error, this is how typically we do it. So y minus y hat, which is the error. So we are going to square them up, error square. So this is going to be squared. Each value is going to get squared. Now, mean of squared error is simply going to be like this, MSC, which is sigma EI square divided by n. Now, when you square them up, what happens? All the negative values will get nullified automatically. So the sum of squared errors divided by the total number of observations. Okay, let me put it in capital form. So this is the capital N over here. So this is called as mean squared error. But this is on square term. So to bring it to the linear term, we take the root of it. We call this as RMSE. Root mean squared error. So this value, RMSE, should also be very small. Let's say your RMSE is again 10,000 rupees or close to 10,000 rupees. That's acceptable, right? So when we are making a predictions on a scale of lakhs, your error is as small as 10,000, not a big deal. And the last one, the most important, other important metric is called as MAPE. So what is MAPE here? Mean absolute percentage error. So to compute percentage error, so absolute value of EI, so that's the error without the sign. Error in terms of the actual value, your actual value is Y, then this is going to give error in terms of percentage of your actual value. Multiply this by 100, so that would convert this proportion into a percentage, and you get percentage error and take the mean of it, mean absolute percentage error. Say for example, in this case, the first one, 10,000 divided by original value is 3,80,000. So that's a very, very small value. Let's say this is 0.01. I'm just roughly quoting it. It may not be. It might be 0.02 point something or something. Into 100, 2%. That means for the first observation, our error is 2%. For the second observation also it is 2%. Why? It's just the sign which is different. Magnitude is same. So 2%, 2%, 3%, 4%, right? So for each observation, what is the error in terms of percentage? And we take the average of it. It is called as mean absolute percentage error. So using these error metrics, like when we take an exam, we have been given grades, and from the grades a CGPA is computed, and based on the CGPA you know how good a student has performed. Similarly here, if we have used a linear regression algorithm to make predictions using the test data, using these metrics, we can decide what is the performance of this learning. If these metrics are all small, especially MAPE is very easy. So if let's say the average error is 2.5%, so that means on average when we make a prediction, our prediction has an error of 2.5%. So a 2.5% error is pretty fine. So when you predict a car price which is of 10 lakhs, so your error is 25,000, roughly around 25,000. So that's not a big problem at all. Okay. So when these type of errors are very small, especially the MAPE is very small, That means the learning of this model is very, very good. The algorithm is doing a very good job to learn from the historical data and automatically from that learning make predictions for these observations, and those predictions are very informative. Those predictions are very accurate. Okay, there are a couple of questions now. Let me visit the questions back. Okay, so there is different types of learning. There is a question on AI, like how a chess game is modeled using data science. It can be done in both the ways. One, using the machine learning way. Using this machine learning way, you create historical data of all the steps taken and the final outcome, whether we won the game or we lost the game. So it would probably have a billions of steps, and each step, what is the stage of the step, and whether the final result is a won or a lost. From that also, we can try to learn how to make the best moves. But the other way of learning it is, given a particular step, you try to foresee what are all the possible steps, and you take that step which will try to maximize your winning. So this is called as the knowledge representation, a different form of AI. That's not machine learning, right? So you try to look through your search space of all possible steps that you can take one of those steps that could maximize the potential of winning the game. So every time when you want to make a move, you try to take it by taking the best step that maximizes your chances of winning the game, right? So those type of learning is slightly different, and it is going to slowly learn by playing the game by itself. It's not taking the historical data, but it is trying to learn by playing the game on its own. That's a slightly different version of AI. Okay, that's not machine learning, because we are not going to talk much about AI for today. Let's stick to that point. Then we can, when appropriate time on the last day when I introduce you to the basic concepts of AI, yes, we can talk about it. Yeah. But for knowledge representation, yes, you need to build in a knowledge base which talks about what is the game of a chess, what are the rules, and what are the valid moves for a given coin. Maybe I'm not representing it as a coin, but whether it is a pawn or a minister or an elephant, right? Each one of them has their own rules. So you need to first build in all these knowledge base. From that knowledge base, you have to decide what would be at a given step, at a given stage of the game, what is the right move so that you better win the chances of the final outcome of the game. Okay, so that's a different kind of AI. But yes, they do that exists, but that's not machine learning. Then what is machine learning? Machine learning is, if let's say somebody played a million games in the past, every move of those games is stored in a database in some form. Now that's a huge amount of data to learn from, and for each game there is an outcome which says whether the person playing the game won or lost. Now, at different stage, what are the moves made by it and what was the end result? From that, let us try to learn what is the right move at a given stage of the game. That's definitely a machine learning. You have a past historical data. From that historical data, we are trying to learn what are the right moves, and we are making the decision based on given stage of the game. Okay, that's slightly different. Hopefully that answered your question. Now coming back to the next problem. So these are the metrics that typically we use for the regression problem. This is only the regression part. So we are still discussing about supervised learning. So within supervised learning, there are two types, regression and the classification. So we simply spoke so far about regression, where our target variable y is continuous. Now, let's talk briefly about classification. Now, what is a classification here? Let's say someone taking a loan from a bank. What is the salary of this person? What is the loan amount? What is the age of this person? Number of dependents, etc., etc. Few more, and whether the person is going to default the loan or not. So there would be historical data which says salary is 25,000, loan is 4 lakhs, age is 32, dependents 4, and this person has defaulted. Another person salary is 32,000, loan is 2 lakhs or 2 lakhs 50,000, and age is 28, dependence is 3, and non-defaulted, right? So here, if you look at this target variable y, it can take only two values. Like it's like a binary data, 1 or 0. Default is 1, non-default means 0. So this is called as a binary classification. Okay, so when your target variable takes values like 1 or 0, that's a binary classification for us, when y can take values like 0 or 1. So these are all input variables over here, which are typically represented by x. Procedure is going to be absolutely same, 1, 2, 3, so on up to, let's say you have 10,000 observations, and I'm using 10,000 observations as a rough value. It doesn't have to be 10,000 always. This is typically called as a sample data, and depending upon the scenario, we have to choose the right sample. And I'm choosing my sample as 10,000. In some cases, it could be less than this. In some cases, it could be more than this. Okay, but don't always think that we would only need 10,000 observations all the time. Definitely not the case. Divide this data into 80%, 20%, exactly same process. The algorithm is going to change. So because we are going to perform binary classification, now the algorithm that we are going to use is called as logistic regression, or we can use another algorithm called as decision tree. So either one of these algorithms. So as part of this workshop, we are going to see demonstrations on both logistic regressions and decision tree, and that's why I'm writing logistic regression and decision tree over here. Okay, so when we perform this binary classification, your y takes values like 0, 1, 0, 1, and your y hat, the predictions that we are going to make, will also takes values like 0, 1, 0, 1. See here, so this is our test data. Let's assume that this is our test data, and we have a lot of input variables x, and when you pass this x to your model, and your model gave you these predictions. Okay, I'm representing my model like this. You would see what a model is in our future classes, maybe tomorrow or day after tomorrow. And when you pass this data, it gave you the predictions y hat. Because it's the test data, you have the actual values y, and you have the predictions y hat along with it. Now, if you compare them, if both actuals and predictions are same, that means we made correct predictions. So these are correct predictions. This is a correct prediction. If actual and predictions are not same, so the actual is 0 and the prediction is 1. So we made wrong predictions with these two. So these are our error predictions. So this is your error prediction. Now, for every observation that we have in the test data set that we give as an input to the model, you get your predictions y hats. Then you can compare them, and simply now, what is the performance metrics in this case? Of course, you cannot use the performance metrics of linear regression because they are very different. The linear regression performance metrics purely depend on the calculation of error, which is y minus y hat. But here, you cannot subtract these things like y minus y hat, which doesn't make any sense, right? So simply, we go with our performance metrics like this. One is accuracy. Accuracy is total number of correct predictions divided by the number of total predictions that we have. So in the test data, let's say we have 2000 observations. Out of 2000 observations, we got 1500 observations correctly predicted and 500 observations wrongly predicted. That gives us an accuracy of 75%. So how accurate we are? 75% of the times model, the algorithm which learned from the historical data made correct predictions. Then another metric, the error metric here, is called as misclassification rate, MCR. Okay, misclassification rate. That's what we call it, or simply people term it as error. So the misclassification rate is total number of error predictions divided by total predictions. In another way, it's 1 minus your accuracy. So if your accuracy is, let's say, 0.75, then your error is going to be 0.25. Okay, so these two metrics are typically used along with the classification problem. So if we are using classification problem and then we are predicting classification, our performance is measured either using accuracy or error. There are a lot more advanced metrics that we use typically in the industry, but for a beginner, you probably don't have to get to that level right away. As long as you can learn from a historical data using an algorithm like this and try to make predictions out of it and measure the model performance using these two metrics, accuracy and error, that's a significant achievement for itself for the people at your stage. Being students, I would definitely appreciate if you could reach to this stage. Okay, so in the next few classes, from tomorrow onwards, what we are going to spend time on is how can we perform all these things, starting from taking small data, taking few observations, understanding the problem, understanding what we are going to predict. Oops. Okay, understanding what we are going to predict and try to build that prediction using Python as the programming language. Like, you read the data into Python because you typically get the data in the form of an Excel sheet or in the form of a TXT file or a CSV file, right? You probably cannot use that directly into your model. So you need to first, get the data into Python first and do some sort of, data into Python, then some sort of data cleaning, because data will never be in a shape and size that you could readily use it. There will be a lot of garbage in the data, so some sort of data cleaning. Then after that, to understand the data, we need to perform data analysis a little bit. This is where you would be building a lot of visualizations. A picture speaks more than 1,000 words, and that's very much true with the data as well. So you cannot understand the data as it is, but if you could try to build some visualizations, some plots, some charts, some graphs, that would help you to understand the data so very well. And finally, after doing all of this, you try to build your model. And this part is typically the most important part, but we would see all of this through different exercises from tomorrow. I have an expectation that people who are participating in this workshop, most of you might have received a 4-hour YouTube video as a prerequisite recommendation. It's about very basic level introduction to Python. Due to the limited time, I may not be able to explain each and every part of Python, and that's definitely beyond the scope. So if all of you could go through that 4 hours tutorial on introduction to Python, that's probably the most crisp and most easiest way of learning Python. And that's one of the best videos available if people are interested in Python. Not just only for data science. Today, Python has become one of the most important programming language even in the software engineering industry. So the amount of time and effort that you spend on learning Python is not at all going to be wasted. And the time when you start looking out for your job, the moment you have Python as one of the programming skill present in your resume, you would find out how valuable Python is. So irrespective of whether it is data science or some sort of software engineering or data engineering, Python is essential at all these places. So my sincere request, spend time, try to complete that 4-hour tutorial before our next class tomorrow. In tomorrow's class, I will try to introduce you how to set up Python, how to start using it. You don't have to practice along with the video today. You just listen over through that 4-hour video. You just understand the concepts through that 4-hour video. That's good enough. From tomorrow, I'll start with how to set up Python, how to use Python, and how to bring data into Python. And then we reach out to the stage where we try to build a model. It could be regression or it could be classification. And one last topic to wrap up. We have 10 more minutes for today. Unsupervised learning. We haven't talked about it. And we would be learning one of the unsupervised learning technique as part of this workshop that is called as clustering. Now, in unsupervised learning, there won't be any outcome variable y. There is no y. It's all x. You have only input variables. Same, let's talk about customers of a bank. A bank has a lot of customers. They have this information about the customer age, account type, whether they have any loan with the bank, or some salary, because salary gets credited into the bank, so they know the salary of the person, etc., etc. All of these variables are x. Now, the bank may have, let's say, 1 million customers. 1 million. 1 million is 10 lakhs. 10 lakh customers. Now, they cannot manage all the 10 lakhs customers as like one single layer. They want to arrange their customers in a way like in the form of tiers. For example, tier 1 customer, tier 2 customer, tier 3 customer, so on. Why? It helps them in operations. If someone walks into a bank, especially when you walk into very big branches in cities, you have different sections in the branches itself, right? You have a separate section for regular accounts, then you have a separate section for wealth accounts, then you have a separate section for privilege accounts, etc., right? So these are the kind of tiers that they have created for themselves so that they can manage their customers very well. Now, a customer walks in, someone who tries to receive the customer, they check, okay, what type of account they have, the regular account, they will direct, okay, go to this block. If someone is a privilege account, so they would say, okay, sir, you are a privilege account holder, please visit this particular counter or this particular block of the bank. Someone is a wealth account holder, it depends from one bank to another bank. Now, this is probably the most privileged of accounts the bank, any bank can give. Now, they would say, okay, directly, please walk into the manager cabin to discuss anything about your account. You have any issues, right? Now, how did they create these type of accounts? So this is like, we have customer information, customer number 1, 2, 3, 4, 5, all the way up to 1 million, which is 10 lakhs. We want to group the customers based on their similarity. All the customers who have similar characteristics go together. So this is all the customers who have similar characteristics. This is one group. These customers are having similar characteristics. So this is another group. So these are all customers are having similar characteristics. This is third group, right? So arranging observations based on their similarity is typically called as clustering. And why it is unsupervised? We are not trying to learn to predict any Y. So there is no prediction here. We are not really making any kind of prediction. We are not learning from examples to predict future. We are arranging the observations based on their similarity. Now, they might have 1 million observations, they might have 1,000, or they might have 100 million observations, etc. Doesn't really matter. Based on the similarity of their observations, based on the similarity of their behavior, we are trying to arrange them into some groups. Within the group, all the customers exhibit similar characteristics. So that's why we are grouping them together. After arranging them into groups, by looking at the characteristics of the group, we can say, okay, these are the characteristics of this group. So this is a tier 2 group. These are the characteristics of the group. So this is, for me, is a tier 1 group. So these are the characteristics of the group. So this is a tier 3 group, right? Typically, this will help the businesses in marketing. It can help them in customer management. We call this as customer segmentation, etc. Right? Different names in the industry, but all of them boil down to how do we organize a group of observations. Here, each observation is a customer. A group of observations into multiple smaller groups in such a way that all the observations in the group are very similar in terms of their behavior, right? So that's why unsupervised learning. We are not trying to learn from the historical data and make any predictions into the future. So simply speaking, if there is no outcome variable, the other name for this is called as target variable. If there is no outcome variable, or if there is no target variable, it's called as unsupervised learning. And one of the popular techniques out of this is called as clustering. And there are different types of clustering algorithms, many of them. In this workshop, we are going to see one of the most popularly used clustering algorithm called as k-means. So this is the heavily used algorithm. So we would learn how to use k-means to organize the observations into smaller groups. Okay, so that's what we are going to learn as part of this workshop. Now, irrespective of what we are going to learn from tomorrow, all the theoretical aspects that I have explained so far is very much important for your data science career. All these definitions probably you have to remember throughout your life. So we started with predictive analytics. Within predictive analytics, there are two major types: supervised learning, unsupervised learning. So within supervised learning, we have two types. One is regression, other one is classification. When do we call something as regression? When do we call something as classification? When we are trying to predict a variable which is typically taking numbers on a continuous scale, that is regression problem for us. When we are trying to predict a variable that is taking outcomes like 0, 1, binary, or it could be 1, 2, 3 also, that is called classification. There are different ways, different algorithms to perform regression, different algorithms that can perform classification. Though both are predictions, not every algorithm can perform everything. Different algorithms for regression and different algorithms for classification. Having said that, there are some algorithms which can do both, advanced ones. Okay, fine. Now, if we build a regression, how do we know that this model is doing good? So we have to follow a process, dividing the data into test and train, and trying to learn from the training, hold out the test, look at the performance on the test, and compute these error metrics. If these error metrics are satisfactory, then you say yes, whatever the learning it has made is good enough. Now, classification. Simply look at the performance, accuracy, error. If this accuracy is satisfied, we go ahead with it. Now, if the objective is not to predict something, instead of predicting, it is like organizing the observations in some way, probably we are looking at an unsupervised learning problem. And for an unsupervised learning problem, one of the algorithms, that one of the objectives is clustering, and we can use the k-means algorithm to perform the clustering. Okay, so this is all what we are going to learn through the workshop, and from tomorrow onwards it's mostly practical sessions where I would be demonstrating them, but if you have to recollect all of these concepts so that you understand the practical sessions very well. Okay, that's all I have for today. I'll still be open if we